All right, so let's talk about the last section here is on inverse functions. And basically the premise is the following. What we've been doing so far with functions is starting with an input and taking f of that input to find the corresponding y value that would give you a point on the graph. Now what we do is ask the opposite question. If I gave you if I gave you a y value, what x value would have had you have taken f of to get to it? All right, so what do I mean? Let's look at this first example. If we just consider this example of a line, we know that if I gave you various values of x, you can find the corresponding value of y, no problem. But if I suppose I started here with a y value, right? Suppose I gave you -3 here for y and asked you, well, what x would you have to have used to get that particular y? What you would do is just solve the equation for x, right? And that's what I'm doing here, but just for a general y. If you have this guy, I'm going to solve for x in terms of y. So I'm going to multiply both sides by 6 and subtract 2. And notice that what this is, if I gave you various values of y now, it's very simple to find those corresponding x values, right? And so what this is a function, right? It's another linear function. And observe that its relationship to the original guy, right? So if I looked at this sort of computation here, g of f of 4. If I compute f of 4, just put 4 in for x, you'll get 1 as an output. And then if I go back and take g of 1, g of y is the function I'm calling by this expression, what I solved for x. G of 1, if you put 1 in for y, you get 4 back, right? And if you did it the opposite direction, had I taken g of 4, right, and I would get 22, and then if I took f of 22, you put 22 in for x here, I get 4 back. So what you notice is that if I apply one function and then the other, you get back the original input, right? And so it undoes, or it takes kind of the inverse of the original function. If you do that in general, for any y you want, if I take g of f of y, that means I'm plugging this f of y in for the input into g of x, right? So I'm plugging it in for this guy here. The 6's cancel and the 2's then will cancel as well, giving you the input y back. And if I do the same thing here, but in the opposite order, f of g of y, I'm plugging in the expression for g of y into my formula for f, I get y again. So whenever this happens, for any input for which the functions are defined, we call them inverses of each other. All right, and so then there's a couple of natural questions to ask. One, can you always find this sort of inverse? Does it always exist, right? And so let's look at this example. Suppose I gave you just a parabola, right? Remember, that's just a U-shaped graph, right, like that, opening upward with a vertex at the origin. Oops. We want to be able to find, if I gave you a y value, what x value would have generated that y. The only problem here is that if you solve the equation y equals x squared for y as I do here, you just don't get x equals a single quantity, you get two of them. You get plus or minus root y. And so the problem is we don't know which x value came from. It could have come from one or the other. And so that non-uniqueness causes a problem, right? And so what we'll say in that sort of situation is that there can't be an inverse function because there's an ambiguity. And in fact, if you try to graph this, right, if you were to take both those pieces and graph them on the same set of axes, what you would get is radical y, which will look like this, and negative radical y flips it over the x-axis. It looks like this. So you get a sideways parabola, and we know that's not a function. It doesn't pass the vertical line test, right? So that that ambiguity kind of manifests into a output that isn't a function. All right. So how do we know in advance, right? How will we know that happens so that we don't try to bother ourselves with finding an inverse if it doesn't exist? And so here are some examples of functions that have inverses, right? So here is a function, right? That was our original guy. and its inverse is this one. Same way here, if I gave you this function, its inverse turns out to be that guy. And so what you're doing, excuse me, here is reflecting one graph over the y equals x line to get the other graph. At least that's what we observe here. But if we do this here, there was my x squared I was talking about. Here's that radical y and here's that negative radical y. They are reflections over the y equals x line. The problem is this one isn't a function. Okay? The difference between these two is that this original function and this original guy pass what's called a horizontal line test. For every input, there's only one output. This guy does not. For any output, there are potentially two inputs that would have generated it, right? And so if there is a horizontal line that hits the graph in more than one spot, then it's not so-called one-to-one. It'll result in this situation where you generate this non-function sort of graph when you reflect over the y equals x line. All right. So let's look at this. Let's actually talk about this together. What I'd like to know is if I were to give you these functions, which of them would have been one-to-one? Which of them passed the horizontal line test? And in so doing, have an inverse. Because we know that to get the inverse, at least from the observations we've made, you would reflect the graph over y equals x. All right, so let's talk about the first one. This one here does not pass the horizontal line test, right? There is at least one horizontal line that hits the graph in more than one spot. If you try to reflect this over the y equals x line, what you'll get is a kind of a circle that opens up this way, right? And so it won't be one-to-one. So this guy is not one-to-one and hence has no inverse. This one here is one-to-one, right? No matter what horizontal line you take, it only hits the graph in more than once, in exactly one spot rather. And so it has an inverse. This one does not, right? There's a little parabola part down in here where it wouldn't pass that horizontal line test. So that is not one-to-one. These two here, if you think about it, those are not one-to-one either because they each contain horizontal segments. So not only does the horizontal line hit the graph in more than one spot, there are horizontal lines that hit both these graphs in infinitely many points. And so it's not one-to-one in a very big way, right? Reflecting both of these over the y equals x line would produce parts of the graph that would be actual vertical lines and not functions in a big way. This guy is one-to-one. Again, it passes the horizontal line test. All right, and so here we have a theorem. We're not proving this theorem, but we have a theorem that says if the function's graph is one-to-one, so in other words, it passes the horizontal line test, then when you reflect it over the y equals x line, the result is a function. That function is the inverse. And so we're piecing these together to say that an inverse function exists if and only if the original function passes the horizontal line test. Since what we're claiming is the way you get the inverse is by reflecting over the y equals x line, note if you look back at those points, reflection over the y equals x line each time basically results in a point where you simply reverse the x and the y. So here you have -2, 0 on the graph. On its inverse, you have the exact opposite, 0, -2. 0, 1/3, 1/3, 0 on the other graph. And that's true no matter what function you take and reflect it over the y equals x line. So that tells you a method by which that you can use to actually compute an inverse, right? All right, so we'll come back to this relationship in a minute. We know that's not one-to-one, so there's no inverse. All right. What this is doing, so I want you to go through this, but it basically just walks you through a couple more of examples of what I just said. It has you graphing a pair of functions each time on the same set of axes. You're verifying that they undo each other algebraically by composition. And then you are noticing that they are indeed reflections of each other over the y equals x line, right? So we're doing that for a couple of lines. Just do that. And then also this one here just take some time, so I'll leave you, the answer is in your manual, but I'll actually pause here just so you can see it to check yourself. All right. And then for this one, we're not graphing, right? This one we're not graphing, but we're actually verifying. Ben, Kipper, stop. We're actually verifying, Benjamin, that they're inverses by computing the composition each time. Sorry, my dog is being a pain. Benjamin. All right. All right, so take a look at that. It's just an exercise in algebra is all this one is. All right, so let's go through how do you find a formula for an inverse function if it happens to exist. So at the moment, we don't know how to graph this function, so we can't verify unless you use a calculator that it's one-to-one. So I'm going to assume that we have that in place. I'm telling you it's one-to-one. We'll see that later. But now we want to find its inverse, and we want to compute the inverse or the function's domain and range. All right, so we saw before, at least in our very first example, what a suggestion was in terms of finding an inverse. The idea is to find a value of x that gives you a particular value of y, right? And so what that means is you want to solve this equation for x, all right? And so let's do that. I'm going to multiply both sides by x minus 3. I'm going to distribute the y through, and then I'm going to take any term without an x to the right side, like I did here, and then just divide by the coefficient of x. All right, and so this expression here gives you the x value for a particular y. And so the inverse function is exactly this rational function here. Don't worry about the fact that I'm using a y here. The y is a dummy variable, right? I'm using it deliberately just to make you realize that this is a given output, right? And we're trying to, when you find an inverse of something, that value is an input. It's an x value of the original function. That's the only thing I'm doing here with why I'm using y. But you could very well, once it's all said and done, you can just replace the y by an x and treat it like you would normally a function. Since geometrically you're interchanging the x and y to find an inverse, the domain and the range of each flip, right? So what that means is whatever served as an x value for f will now serve as a y value for the f inverse, and whatever served as an output for the original function f will serve as an input for inverse, right? And so that's what this means. Remember, the domain is a set of inputs, so the domain of your inverse function has to be the range of the y, of the f rather, right, the original function. So the x values that work for your inverse are the same as the outputs that you got from your original function f. And same way here, the outputs that you get from the inverse function have to coincide to the inputs you used for the original guy. All right, and so this is easier now to find what the range of the function, the original function is. It's simply the domain of the inverse. And for a rational function, remember, the domain is simply the values for which the bottom is not 0, namely everything but 0 itself in this case. And so that means the range of the original function is all real numbers except for 0. All right, so why don't you try these? So I'm gonna have you pause the video at the moment. This one is routine, so this would just kind of get you warmed up. Number 2 is very similar to what we just did. Number 3 isn't bad, but it has an extra x value, so it causes a little bit more grief with the algebra. So go ahead and try to find an explicit formula for the domain, or sorry, for the inverse functions for each of these, and then find the domain of both the function and its inverse, and then we'll talk about number 3 after you come back. All right, so if you want to check yourself for 1 and 2, here, just take, pause the video at this point so you have the whole thing on your screen. All right, but we'll talk about number 3. All right, so here we want to find the inverse for that rational function. And so what we're going to do is solve this for x. Okay, so let's do that. Enlarge that so you can see it. So to solve that for x, I'm going to multiply both sides by the denominator. I'm going to distribute this y through. right? I'm going to pull anything with an x to the left and everything without an x to the right. So I did here. Factor the x out, and then divide by that y minus 2. Right? So this function here, right, so namely f inverse of y would be this right-hand side. Notice here I replaced that y by an x, like I said. Remember, it's a dummy variable, so it does not matter what variable you use. This is the inverse function. The domain of the inverse, it's a rational function. The domain of this function is the set of all real numbers except for 2. But remember, the domain of the inverse is exactly equal to the range of the original function f. And so the range of this function is the same. It's everything but 2. And then likewise here, the domain of the original function is everything except for minus 7, but that corresponds to the range of the inverse, right? That's that dual relationship between the two. All right, and that brings us to the homework problem section. All right, so key takeaways. A function is 1-to-1 if and only if it passes the horizontal line test. If it passes the horizontal line test, it has an inverse. To find the inverse, you set y equal to the function and you solve that equation for x in terms of y. Once you have that, that gives you the inverse function formula. All right, so go ahead and try these problems. Very much similar to what we just did. A couple of interpretation problems, number 4, number 6, to get you thinking about what you're really doing. Remember, the inverse function gives you a input, right? So E inverse of x is an input into the original function, right? So think about that when you're doing number 4 and 6. All right, let those do those and let me know how it goes. All right, see you later.